Hello everyone and welcome back to the channel. As you can see, my sunburn has really not faded at all after a week and a half. And my face is currently the same shade of red as the Netflix logo. But today we're going to be doing yet another systems design video. I recently acquired a copy of the Alex Zhu book, which has given me some more inspiration for problems ideas. So today we're going to be doing a payment processing system for an e-commerce website. Now, I had always thought about this problem, and a lot of people had asked me to make it before, and I always thought it was kind of dumb because I was like, well, just go to Stripe. But then, I got some inspiration and realized that the problem is a little bit more complicated than that. So today we get to go through all of those failure cases and talk about them in depth. Okay, so as previously mentioned, today we're going to be building out the internal back-end payment system of an e-commerce site like Amazon or Temu or Rakuten or anything like that. So the gist is, if I'm a user and I'm about to pay for an item of carts, we've got my confirmation button over here. We've got some confirmation of which card I'm about to pay with, and then also an itemized list of the items that I'm paying and perhaps even the sellers that money should be routed to. Cool, so let's go ahead and formalize some problem requirements. So like I mentioned, this is for an e-commerce site, and two of the main things that we want to do is, number one, we want to basically account all of the payments for all of our buyers and also all of the profits for all of our sellers. And ideally, those should be ordered by time so that we can quickly figure out over a given time range how everyone is doing in terms of how much they're spending and how much they're making. Additionally, it's very, very important that for an e-commerce site like this, we have a perfect record of all orders and payments. We do not want to lose any of that data because otherwise customers are going to get very angry, and that's when we get sued. So another thing, besides not allowing anyone to lose their data once they've submitted an order, is that we don't want to allow duplicate orders as well. If I'm a user and I click the submit button and then I click it again, I shouldn't pay twice. The system should stop me from doing that. So no double submitting payments, aka we want idempotent payments. And then finally, I'm not actually going to talk about building out the actual payment service itself. Because the United States credit card network is a complicated thing. It's a bunch of APIs. I don't want to talk about dealing with bank accounts, not only because it would be boring, but because I don't know how to. And if I did, I would be a wealthy man. So we're going to assume basically that for any payments from the users to us, Amazon, the middleman, we can use something like Stripe. And then for any batch payments that we make to our vendors, we can use something like Potentity. Cool. So let's now go into some overall design considerations. I'm not going to draw out any high-level diagram just yet, but hopefully this could maybe contextualize the problem for some of you guys and give you some hints into where we're going to take this thing. So number one is that we really don't care about latency, right? I mean, we do. We want to make it as good as possible, but at the end of the day, we said we can't lose data. And so what that means is that even if it takes a few seconds for a user to submit their payment information, that is totally okay. We care a lot more that they're never going to lose that payment information, and so we're going to optimize for that. Number two is that we can't approve all payments instantly, right? Some credit cards may get flagged as potential scam payment, and so maybe Stripe is actually going to take a few hours or maybe even a couple of days in order to actually approve a given payment and then send notice of that back to us. They might just say, hey, for now, this thing is pending, and you're going to have to deal with it later. Number three is that as long as we have one source of truth table, right, with all of our pending payments and our accepted or failed payments, everything else that we have can be derived off of that, right? We basically need this one ledger or this one payments table, and then we can use derived data that we've used plenty on this channel before. As we all know, I'm a flankophile, and you can basically ship all that data and all those changes into Kafka and then make a bunch of other databases that are reading from Kafka and ultimately making their own views on top of that data. So the first question is, well, if we need to have one table that's effectively perfect, right? No lost data, it has to be the source of truth. How would we actually go ahead and do that? I guess the thing that should pop up in your head is using some form of consensus, right? So we've got a couple of options. One is just to use strong consistency via synchronous replication. So let's imagine I have a leader database over here and I have a follower, and then I have a client. What synchronous replication says, as we've covered many times on this channel, is a write is not considered valid on the leader until it has reached the follower has acknowledged it, and then finally the leader can return the status back to the client. So we have to go 1, 2, 3 for the acknowledgement, and then 4 for the acknowledgement from the leader back to the client. Now the problem with something like this is that we have absolutely no fault tolerance whatsoever. If the leader goes down, we can't make any writes. If the follower goes down, we still can't make any writes. So that's going to be a problem. Sure, you could perform failover on the leader, but now you don't have another replica to write to, and so as a result of that, again, no fault tolerance, synchronous replication is not going to do it for us. So now what you might be thinking of is, how have we talked about achieving strong consistency in the past while actually having some ability to lose nodes or, achieve some fault tolerance? And the answer that we've at least spoken about is using distributed consensus algorithms. So one that we've covered in depth on this channel is Raft, but you could also use something like Paxos or Zab, any similar type of algorithm. And so the way that we would do that is on the replication log. So in the past, we've mentioned that these types of distributed consensus algorithms are used for multiple nodes to make sure that they can basically write one type of log, and then as long as one write is committed in that log successfully by the algorithm, we know that it will never be lost. I mean, it can be lost if I were to go up to all 3 computers, for example, and hit them with a hammer, but the point is it's very, very unlikely, especially if we distribute where these computers live, and if we're only talking about something like disk failures or networking failures. So how's that going to look? Well, if you recall, basically to very, very quickly summarize Raft, you have some sort of leader node, you've got a couple of follower nodes, and basically, in order for a write to be committed, it needs to first be acknowledged by a quorum of nodes in your cluster. So if we have 3, that means that the write has to go through successfully on 2 of them. And so for that write to happen, first, our leader gets the write, it proposes it to all followers in steps 2A and 2B. This guy is down over here, so it's never going to respond. And then the top leader, or rather the top follower, is going to respond successfully. So the leader says, okay, go ahead and commit this thing. Once it gets an acknowledgement that the write has been committed to the follower and the write has been committed to itself, it can go ahead and tell the user, hey, your write was successful. Now the thing that you should note here is that even though this is a great way of ensuring that all of your writes are going to be persisted to at least a couple of nodes, and that even if the leader goes down, that write will still exist and continue to exist in subsequent epochs, the problem here is that we are sending a lot of messages over the network, and so this type of process is very slow. If we expanded our cluster size from 3 nodes to 5 nodes, again, we have more fault tolerance, but even still, our writes become slower and slower. So fortunately, that's not our main concern for this type of problem, but we will talk about how to make that type of write a little bit faster later in this video. So the next piece of the puzzle that I want to cover, now that we've talked about strong consistency a little bit and how we can make sure that all of our writes are persisted, is actually making payments idempotent. So typically, when we want to make something idempotent, we basically have 2 options. One is to do something like a 2-phase commit, right? Where I can say, well, if you're the user, and you're trying to submit a payment, when you put it in the database locally, you also have to put it in Stripe's database, and it's got to work at the same time, and if it doesn't, you're in trouble. In reality, that's going to be a slow process, and in addition, we can't just go access Stripe's internals, so we have to go along with what they ask us to provide, which is an idempotency key. So the idempotency key works because, if we provide the same idempotency key for a transaction twice, Stripe is going to take a look back at us and say, hey, I've already seen this one. This is a duplicate payment. I'm going to ignore it. Cool. So how will we actually generate an idempotency key? This is another piece of the video that, although I could go into it for plenty of time, I won't, because it's effectively the same thing that we did in our first systems design problem on this channel, which is the tiny URL problem, which really means we basically have 2 options. One is that we can pre-materialize all of our idempotency keys, right? We create a bunch of random keys, we split them out onto a bunch of servers, and then every single time someone requests a new idempotency key, the server is basically just going to assign that request the next unused idempotency key. So that's one option. Another option is for all the clients, when they request an idempotency key, to first basically generate some sort of hash. Maybe it's based on the user ID, maybe it's based on the timestamp that this request is being submitted, because ideally we do want as few collisions as possible, so something like a hash could be nice. And then basically it's going to go to the database, say, hey, I'm trying to claim this idempotency key, and the database, assuming that we're doing some sort of locking, or maybe it's a SQL database that's enforcing primary key constraints, is going to tell us whether or not that key has been taken. If it has been taken, maybe we bump that number up by 1 and try and take the next key, or something along those lines. So in that case, we would probe for the next available. Now, of course, this is only going to work if every single time that a client generates a key, if 2 clients generate the same key, their request needs to go to the same database node. So we have to partition in a smart manner. That's partitioned by the value of the key itself, or maybe a hash of the key. Otherwise, 2 requests could go to separate database nodes and they might not know about one another, and then they're both assigned the same idempotency key. Cool. Another thing that we can do to make our table reads a little bit faster is we can actually go ahead and index that table based on that idempotency key, because basically, we want a database full of idempotency keys. Eventually, we're going to have to check whether a given idempotency key exists when we hear back from Stripe. And so we want to basically index our table by that key value so that we can quickly find its location. So like I mentioned, we have this one table, this centralized payments table, or maybe we can call it a ledger table, or even an orders table. But the gist is we have one table that is strongly consistent. And so if all the writes are going through it, that basically means they all need to be ordered in one sort of distributed log, and that is going to be problematic and hard to achieve. So what would actually be better is basically if we could somehow increase both the write and read throughput of our system. And the way that we might be able to do this is by using partitioning, right? So basically, instead of just having one payment table like this guy, we can have a second one, and then each of them is effectively running their own Raft algorithm to make sure that all of their writes are strongly consistent. Now, the nice thing about this is this could get a little complicated. If we had to do any cross-partition writes, then we would have to introduce some two-phase commit into the equation. But the nice thing about payment writes is that we're just creating one row at a time, and we're just modifying one row at a time. So as a result, basically all of these writes are independent to one another. So in theory, I would think that our throughput would scale linearly with the number of partitions we have. So of course, we'll have to experiment with that, but it should be a nice solution. So basically, like I mentioned, what we want to do is probably partition our nodes by the hash range of the idempotency key. This way, they're distributed relatively evenly. And also, again, it means that if 2 users were to attempt to claim the same idempotency key at once for their incoming transaction or for what they're about to submit to Stripe, they would both be routed to the same database node. There would be a conflict, and only one of them would be able to claim that key. Cool. And then assuming we did the pre-materialization strategy where it's not clients generating their key, but it's actually the database generating it, what you could do is basically just round robin requests from the load balancer to try and evenly distribute load across using one of those databases. So again, that should help us to scale out our throughput quite a bit. Okay, so let's now, finally that we've introduced kind of these opening concepts, go over a pretty simple design for how we're going to try and handle all this payment information. So step 1 is basically we have a client over here, and he finally lands on that payment page. He's selected which products he wants, and he's just opened up the confirmation page. The second that we open up the confirmation page, we want to generate our idempotency key. The reason being that if I'm going to click the payment button multiple times, it's going to be from that same confirmation page, and so I can't just generate the idempotency key. When we click the button, we have to generate it based on the actual payment page load itself, and then store that locally in the browser. So we create our pending payment the second we land on this confirmation page and get the idempotency key. How do we do that? Well, we go over here to our payments database. So now what we might have is something that says like key is 1234, payment is $10, and right now it's pending. Cool. So now in step 2, we take our payment server, and what we're going to do is go to Stripe with our idempotency key. Now at some point in the future, Stripe is going to do a bunch of stuff, and ideally it's going to get back to us, right? We're eventually going to receive some sort of notification from Stripe, and we'll talk about that in a little bit more, with our idempotency key attached to it. You can go look at the Stripe docs. This is very much how it works. Now our payment server receives that. We're going to go update the status in the database. Hey, this thing is no longer pending. Now it's completed. And then using change data capture, we can basically sync all of this data to our other databases and derive more data from it. Hopefully that makes sense as a really high-level overview. However, there are a lot of systems involved here, and that means we can be prone to failures. So let's go ahead and talk about some of those. So, for starters, what I first mentioned in the overview section was that Stripe does not process all payments instantly. So in step 3 over here, we're not necessarily going to get back this message instantaneously from Stripe after step 2. It could be an hour, it could be a day, it could be a week to process that payment. So actually, what Stripe does in their API is you can basically give them a URL, which is known as a webhook. So what a webhook really does is, I expose an API from my server, I tell Stripe the name of that API, and then when Stripe completes a certain request for a payment, it'll actually go ahead and call my API with the necessary information that it exposes. So Stripe is going to hit that on completion. So this way, even if we don't receive word of whether a payment was completed or failed instantly, our server always stays ready to receive it. Great. So what are the failure scenarios now that we've kind of explained how we're actually going to hear back from Stripe? Well, for starters, number 1, what could happen is step 1 goes through, right? We get our idempotency key, we put something in the database with a status of pending, and now after that, maybe our payment server dies and we never actually submit it to Stripe. So that's failure scenario number 1. Failure scenario number 2, which is also going to be a problem, is that, because of the fact that, we submitted step 2, we said to Stripe, hey, go process this payment for us, and then Stripe has some sort of webhook saying, hey, we're going to reach out to this particular payment server right here, some URL that it exposes. However, maybe our payment server went down, and as a result, now there's no webhook that's actually exposed. So we never hear back from Stripe. So what can we do to fix these? I think, in my opinion, the best answer here is pretty naive, and it's just going to be polling. So on some infrequent interval, basically we want to look at all of those pending transactions in our database, anything that hasn't yet been completed or failed, where we haven't heard back from Stripe. And then we want to go ahead and ask Stripe, hey, what happened with this? You can still poll Stripe for sure. It has APIs that allow you to do this. So the first thing to note is that we should probably only do this for pending payments where some amount of time has actually passed. The reason being that if we go to Stripe and we say, hey, what do you think of this payment? Has it completed or failed? And Stripe says, I've never actually heard of this payment ID or this idempotency key. Then you're going to say, oh, then you know what? We must have actually never made it to Stripe for this one. Let's go ahead and delete it from our database. However, if you do that after like half a second from when you added it to the database, what could happen then is that Stripe just has yet to hear about it. It could be a slow network connection and hasn't yet told us that the payment is valid. So you may want to wait some amount of time before you actually start asking Stripe about a payment. Maybe 10 minutes, maybe an hour. You could configure this in practice. So what do we do based on what Stripe tells us? For starters, let's say Stripe says, hey, I've never heard of this payment. I don't recognize this idempotency key. Well, that means that it probably never reached Stripe. We should go ahead and delete it from our payments table. It's not pending. It just never even got there in the first place. Number 2 is a completed or failed status from Stripe. Then what we would want to do is go back to the payments table and add the completed or failed status. Seems simple enough. Number 3 is Stripe says, hey, I'm still not sure yet. We're still processing this thing. Do nothing. We'll pull for it again, maybe in another hour. That's totally fine. So another question is, well, okay, we want to only do this for our pending payments where they've lasted for some time, right? They've been pending for maybe an hour already. Then we want to start polling. How do we quickly figure out which payments these are? Because like we mentioned, right now we're using a database that is strongly consistent, and as a result of that raft algorithm, writes are going to be pretty expensive, and in addition, if we want to make a good read from our database, we would have to grab some locks on the data, and now all of a sudden we're interfering with writes. So what can we do instead? Well, what I propose doing is creating a pending payments cache. The reason being twofold. One, we can store our data in memory, which is going to be faster than on disk, which is how it's going to be stored in the database. Only a small percentage of all the payments of all time will be pending, so I do think it's fairly reasonable to assume that we can fit it all in memory. Number 2 is that, like I mentioned, when you want to make a consistent read and you don't want to read stale data, basically you would have to lock on your database node to get a good read. Otherwise, incoming writes could modify or mess with the data that you're reading. So you don't want any contention there because it's going to mess up the write throughput of any incoming payments that new customers are making. So what we would prefer to do is instead basically isolate all of these things in a separate cache. So even though we are going to have eventual consistency here, right, we don't have maybe the most up-to-date view of the payments, we're not going to mess with any locking, and we can read all of these things from memory. And it's totally okay, right? Like if I see a payment marked as pending, but it really has been completed, maybe I go to the database and say, hey, I think this thing is completed now. The database is just going to tell me, yeah, I already know that. Doesn't matter. So what does this workflow kind of look like? Well, we've got our strongly consistent payments/orders table over here. Because of change data capture, everything is going to be flowing through Kafka. And then we can just have Flink as a cache where it builds up some stateful cache of all the pending payments in memory. The reason I say to use Flink is so that if it goes down, we can basically restore all that state from a snapshot that we put in S3. And so the gist is, what we can do is as payments come in, we can add them to this linked list, or rather a doubly linked list, ordered by their timestamp. And we can also have some sort of hash map pointing to those payments. The reason we want a doubly linked list with hash maps is that removes from this list are O of 1 if we hear from Stripe that a payment has been confirmed. And additions to this list are going to be O of 1. And additionally, the list is already sorted by the incoming timestamp, so that way we can only poll for payments that have existed for a certain amount of time, and we don't have to sort the list or anything like that. It's just one single part of this list is going to be beyond our threshold, and one is within our threshold, and we can just poll for those idempotency keys. So like I said, we're going to poll Stripe on some sort of interval. Who knows if it's a minute, who knows if it's an hour. You'd have to test this out in practice. And basically, once we hear back for any of those idempotency keys, we can go ahead and write right back to the payments/orders database, which again flows back through CDC and into Flink so that we can update our internal state. Okay, let's talk about derived data a little bit more in general, because like I mentioned, besides just having this ledger table, we want to be able to relatively quickly read certain details about payments for both buyers and sellers, right? So we want both the revenue per seller in one place, and also it'd be good to have either the orders or basically just how much a given buyer has spent in a given time period as well. So for this, typically what you want to do, again, is use change data capture. As long as this guy over here is strongly consistent, we do know that eventually is the key word, all of that information is going to flow through CDC and into our databases that we care about. Eventual consistency is okay here because these are just views for the user. If they have to wait another couple of minutes to see their up-to-date data, that's okay. We just know that this guy is the source of truth if we ever get audited or sued or anything like that. So basically, payments DB gets a change, it goes through Kafka, it goes into some sort of stream consumer, and then the stream consumer, based on both the buyer ID and the seller ID, goes through a load balancer and populates the correct shard of a database. So for example, if we wanted to look at all of the sales that a given seller has had over a month, and let's say that we see one particular order where we've got seller ID 2 just made $10, we consult the load balancer, see which node that goes to, and then write to the particular one. Now, because these are inherently all ordered, because these are all inherently populated with a timestamp, right? All of these messages, time 10, we can order them in our time series database properly. And so as long as we order by that timestamp, now we can really easily and quickly query the time series database for the revenue of a given person over a particular time frame. Alrighty, so let's go ahead and get into the diagram. So as you can see on the left, we have our client. So we're going to go through the same exact workflow that we already did from a high-level perspective, but now ideally we are going to just make it a little bit more specific. So as we mentioned, step 1 is that we have to basically ask our payment service for an idempotency key. The way that the payment service does that is it can go ahead and hit our payments DB over here, which is strongly consistent. Payments DB, strong consistency. That can act as a key generation service. We use round robin to hit one of them, let's say this guy in particular. Apologies for the accidental flick. And then we're going to come back with our idempotency key. We then use that in step 2 to go over to Stripe and give it our idempotency key. In step 3, some amount of time later, our payment service should ideally be hearing back from Stripe, and going to the database to the appropriate one based on the item potency key to either confirm that the payment has gone through or to say that it failed. However, of course, there's always a possibility that this just went down and it never went through. In that case, we want to register change data capture onto our payments database. The reason being that Flink over here can then see that there is actually a pending payment. And so on some sort of polling interval, it can then go over to Stripe, say, hey, is this guy actually confirmed or is it failed? Once it finds out the answer to that, it can too go to the load balancer to figure out the right place that that item potency key lives and update the status. Again, this all flows back through the change data capture for Kafka and back into Flink so that it knows that it no longer has to poll for that item potency key. The second piece of this puzzle is going to be doing all of our derived data. Over here on the right, we also have a stream consumer pulling from Kafka change data capture. This doesn't have to be stateful, it just has to basically forward messages over to our derived database tables. One of which will be the user orders, where we basically shard on the buyer ID and order by the timestamp that it was placed. Number 2 is going to be the seller revenue, where we shard on the seller ID and yet again order by the timestamp that it was placed. Finally, these should probably both be time series databases, but I'm open to potential other solutions. If someone said they wanted to do something more column oriented, maybe put them into Snowflake or a data warehouse or something like that, I'm open to that as well. Anyways, guys, I hope you enjoyed this video and that it was informative. Going to keep looking for more inspiration for problems, but if you do have any, feel free to jump in the comments section and ask me for problems. I do ask that when you give me them, please try and give detailed functional requirements as well, because a lot of the times people will say something and it's not instantly clear to me what the exact challenge is. So, really try and hone in on the difficult part of the problem, and that way I can take a stab at it. Anyways, enjoy the rest of your week. I will do the same, and I'll see you in the next one.